Assalamualaikum warahmatullahi wabarakatuh. First of all, allow me to introduce myself. My name is Fitriani with study ID number 23 TKM 043. Today, I will present the result of my research entitled The Effect of pH and Time on the Recovery Nickel Mangan Cobalt Oxalate Precipitation from any Citrate Solution. The study aims to determine the extent to which variation in pH and reaction time affect the efficiency of NMC oxalate precipitation recovery, as well as to identify the optimum condition for both variables. The background of this research is based on the increasing advancement of technology, especially in the field of transportation such as electric vehicle. These vehicles rely on energy stored in lithium batteries, the demand for which continues to rise. One of the most essential components of lithium-ion batteries is the cathode. Among the commonly used cathode material is nickel mangan cobalt oxalate, or NMC oxalate, known for its high specific capacity, good thermal stability, and lower production costs. Recovering this metal from waste of a leftover solution has become crucial, not only from an economic point of view, but also for environmental sustainability. One commonly used method for this recovery is precipitation, in which pH and reaction time play significant roles in determining the final outcome. The research problem addressed in this study is how do pH and time affect the recovery of NMC oxalate precipitation from any citrate solution, and what are the optimum value of pH and reaction time that yield the best recovery result. In line with this question, the objective of this research is to evaluate the influence of both parameters and identify the most effective condition. And as for the theoretical condition, this research refers to previous study conducted by Ananda et al. 2024, which used nickel and NaOH as the precipitating agent. The findings showed that pH 4 with a duration time of 2 hours, the recovery value reached 53.24. This research was carried out with material and extractive metallurgy laboratory and the basic process and integrated testing laboratory at Polytechnic Makassar, South Sulawesi. Between 14 March until 20 March 2025. The research was divided into two main stages. The first stage was sample preparation, which began with dissolving 200 AdS grams of solid citric acid in 1 liter of distilled water. The solution was heated in 3 neck flash until it reached 70 degrees Celsius, which the target temperature was reached. HP or mixed hydroxyl precipitate obtained from PTK Binu Energy Materials Morwali Central Sulawesi was added, and the reaction time was set for 180 minutes. After that, the solution was filtered to separate the filtrate and residue. The filtrate, which is referred to as the N-acetyl solution, was used for the next step. The second stage was the formation of NMC oxalate, where the N-acetyl solution is mixed with brown sulfate, copper sulfate, and oxalic acid in predetermined weight based on the molar ratio of NMC 811. Once the mixture was completely dissolved, 100 ml from each solution was taken for 9 experimental runs. The solution were heated on a hot plate to 40 degrees Celsius, and then an NaOH was added drop by drop until the desired pH value of 1, 4, and 7 were reached. The solution were then allowed to rest for 60, 120, and 180 minutes respectively. After that reaction, the precipitate was separated from the filtrate. The precipitate were washed several times with hot distilled water, ensure that no impurities or metal residue remained. After washing, the precipitate was dried in oven through multiple heating cycles until a constant wedge was received. The final analysis was carried out using an XRF instrument, Newton Excel versus total analyzer. For the analysis, the percentage of NMC precipitation recovery was calculated using the formula, the mass of the precipitate multiplied by the concentration obtained from XRF divided by the initial metal concentration based on the NMC 811 mole ratio, then multiplied by the initial volume and 100. At pH1, precipitation proceeded this loss with a recovery of 44.30% at 60 minutes and a slow increase to 51.68% at 180 minutes. This is due to the high solubility of metal ion in acidic environment, which inhibit effective precipitation. According to Putri et al. 2023, high ion solubility is caused by low pH level. In contrast, at pH 4, the recovery increased gradually over time, indicating a stable and controlled precipitation process. The recovery value at 60, 120, and 180 minutes were 52.40%, 55.11%, and 57.92% respectively. This suggests the direction moved gradually toward equilibrium without any sign of redissolution of the precipitate NMC. The 180-minute duration allow maximum interaction between metal ions and oxidization, resulting a nearly complete and stable precipitation. These findings are consistent with Amanda et al. 2024, who found that pH 4 was optimal for nickel precipitation, supporting that it provides the most suitable chemical condition and for efficiency precipitate formation. Moreover, pH 4 is more operationally visible in industrial system and compared to pH 7, as it does not require excessive enema addition. This helps reduce chemical costs and enhance efficiency in industrial scale operation. As noted by NASA et al. 2022, on the other hand, at pH 7, inconsistency were observed in recovery value, including a decline at 120 minutes, followed by an increase to 62.40% at 180 minutes. When the pH exceeds 4, metal ions such as nickel 2+, mangan 2+, and cobalt 2+ tend to rise with OH ions, forming an NC hydroxide, which are undesirable. These hydroxide compounds are more difficult to convert into cathode material from lithium-ion batteries. From a cost perspective, using NaOH to adjust pH also show at pH 4 is more efficient than pH 7. Less NaOH is needed to raise the solution from acidic condition to pH 4 than to pH 7, which directly reduce chemical operation costs. Research by NASA et al. 2022 also demonstrated that excessive alkali use increased neutralization, complete complexity, and waste management costs. Additionally, waste from precipitation at pH 4 tend to mildly acidic, easier to treat, and less harmful to the environment. In contrast, was from pH7 contains excess base. Example, Na plus and ohamine, which if not neutralized can pollute water system, harm aquatic life, and cause corrosion to pipeline and processing equipment. Bustiana et al. 2022 report the heavy metal precipitation at high pH level tend to produce residue that are harder to degrade or treat in standard wastewater treatment. And considering the experimental finding and supporting literature, the combination of pH 4 and reaction time of 180 minutes proved to be the most optimal condition for NMC oxide precipitation. Under this condition, the process was stable, efficient, free of redissolution, and produced precipitate that are thermodynamically more favorable for conversion into cathode materials. Therefore, pH 4 and a duration of 180 minutes can be concluded as the optimum parameter of effective and sustainable precipitation of NMC oxide from any citrate solution.